Sehr geehrte Rektorin, liebe Sarah, lieber Onur, liebe Gäste und Kollegen. It's a great pleasure to introduce today our new colleague, Onur Mutlu. Not so brand new, actually. So Onur was elected ETH professor in September 2015, and he started at the computer science department a year ago in May 2016. Onur was born in Kayseri in Turkey, where the kings of Cappadocia used to live. And he then moved to Istanbul, where he finished his high school, actually while his family already moved onward. So early on, he had to learn to be independent. He then started his studies at Bilkent University in Ankara before he took the opportunity of a scholarship to move to the US, to the University of Michigan, where he earned bachelor degrees in computer engineering and in psychology. So Onur has to offer a broad spectrum of expertise from early on. For his graduate studies, Onur went to the University of Texas at Austin, where he defended his PhD thesis on efficient run-ahead execution processors in 2006. And already during that time, he collected industrial experience at Intel, and in fact, his doctoral work has already left its footprints in commercial microprocessors. After his PhD, he started the computer architecture group at Microsoft Redmond, and he then joined CMU, Carnegie Mellon University, in 2009, where he held, towards the end, an endowed chair, the Dr. William and Nancy Strecker Early Career Professorship. His scientific work had impact on and was recognized both in academia and industry, with faculty awards by, and now this reads like who is who of relevant companies, Facebook, Google, HP, IBM, Intel, Microsoft, VMware, and Huawei recently. Right, so who is missing? Onur, actually, for the first time, he came into Zurich in 2014, if I remember right, for a conference, just innocent visit, so to say. And then we tried to convince him to spend his sabbatical at ETH. We failed. But instead, we were lucky and were able to convince him to join ETH and strengthen the computer science, the computer architecture and systems group at our department. So, Onur, we are very glad that your impressive career has carried you to ETH. I wish you the best for hopefully a long and fruitful time at our department and our school. We are looking forward to your lecture. Please.
Thank you very much, Emo, for the lovely introduction. And I appreciate the research that you did into Kayseri. And not many people know that it's where kings of Cappadocia actually lived, I think. So it's a great pleasure to be here. I've been here for a little bit over a year, and I've been thinking a lot about computing architectures. I have too many slides to cover, which means that I will not try to cover all of them, but I will hopefully try to give you the gist of it. If I'm going too fast, you can find the slides on my website later on, and I'd be happy to talk with anyone who's interested in talking about anything related to what I will present. So I will talk about future computing architectures. And the first thing I want to start with was, why do we do computing in the first place? And I think my answer would be to solve problems. But there are other answers which are similar to this. To gain insight was Dick Hamming's answer in 1962. To enable a better life and future is probably a broader answer going forward. Because initially, when Dick Hamming was doing computing, actually computing was more into number crunching And his point was, it's not only number crunching, it's the insight we generate. But today, it's really everywhere. It's everywhere in our lives. So how does a computer solve problems? By orchestrating electrons, at least in today's dominant technologies. That didn't used to be the case a long time ago. And how do problems get solved by electrons? We start with something called the transformation hierarchy. We start with a problem, and we need to communicate to the electrons in the end. So we have built a large transformation hierarchy. We transform the problem into the algorithm, into a program that gets executed on some software, that gets translated into the hardware through some interfaces. And now we're into the hardware domain where we have what we call the microarchitecture, which is like building architecture, except it's designed to execute programs, and then logic, and then devices, and then electrons. So this is the transformation hierarchy. Computer architecture, as a narrow view, has been defined this way. It's not always been that way, but people think usually it's the interface between the hardware and the software and this little layer called microarchitecture. In this talk, I will advocate for a more expanded view, where this is still the core, but you also design across the hierarchy. And I will hopefully motivate this a little bit more. So let me give a more formal definition, if you will. It's not exactly formal, but the way I view computer architecture is it's the science/engineering, and also the art of designing computing platforms, mainly the hardware interfaces, the system software, and the programming models. To achieve a set of design goals, we always have a set of design goals. For example, it could be the highest performance on workloads X, Y, Z. It could be the longest battery life at a form factor that fits in your pocket with costs less than some dollars or Swiss francs. It could be the best average performance across all known workloads at the best performance cost ratio, ... So there is a huge design space. Designing a supercomputer is clearly different from designing a smartphone, but many fundamental principles are similar. And hopefully I'll talk about some of these principles. So these are some of the platforms you may be familiar with, may be using, may not be using. It's another example platform, a self-driving car. It could be used for this purpose also. And we design computers, and they're used for, we may be designing computers for things that we think they will be used for, but they may be used for other things as well. So it's important to anticipate different things. And if you look at a self-driving car, actually, in the back, there's this computing platform that processes a lot of data so that the self-driving car can actually work. Actually, when I was at CMU, Raj Kumar was driving the DARPA challenge, and he was designing CMU's self-driving car, autonomous driving car, in 2008. And if you looked in the back of that car, it had 12 big servers sitting there, ensuring that the computation is done on time so that the car can make the moves. So the key is, how do we enable these computing platforms to enable different kinds of quality of life measures in the future? This is another platform. This is a data center. It looks beautiful. Looks very artsy, but this has a different design goal also. And this is one of the highest performance supercomputers, Tianhe 2, that has a different design goal. And this is one of the most recent ones that had attracted a lot of attention. This is Google's tensor processing unit. Basically, Google figured out that they needed to accelerate neural networks in their data centers because they use that for many purposes. And they designed this chip which achieved 15 to 30 times higher performance than existing platforms today. So hopefully this gives you a breadth of computing architectures that we see today. And this is actually a very good example of why we need thinking across the stack. So I believe Google actually got it right in this case, where they designed this chip to accelerate a very heavy part of their computation in their data centers. And if you look internally, this is a systolic array, which is a very fundamental way of doing computation. But I'm not going to go into that right now. So I will start with this axiom. To achieve the highest energy efficiency and performance, we must take that expanded view that I talked about of computer architecture. Basically, not this narrow view of software-hardware interface and microarchitecture, but a broader view. And co-design across the hierarchy. Co-design the devices with the architectures, with the algorithms together. And specialize as much as possible, of course, within the design goals. This is easy to do if you have a single application that you care about, because you can specialize the entire stack for it. But if you're catering for many, many applications, this may be harder to do, of course. So the next thing I would like to tackle is, what kind of a future do we want? Because in the end, whenever we design any architecture, we're designing for the future, not for today. This is, some of you may recognize this. This is the Tacoma Narrows Bridge, which looked reliable at this point, but it turned to be this way on November 7, 1940. And this is taught in classes in civil engineering and physics, I believe. Clearly, we want a reliable future. You don't want something that may look reliable, may cause security issues and safety issues in the future. And these guys who are building the buildings may be happy at the moment, but are they really safe? So I think I will posit that reliability, security, and safety is a huge challenge and opportunity going forward in computer architectures. And I'll hopefully give you an example of why this is the case. The second feature is something like this. At least I would like this kind of future as opposed to this kind of future, which is like Pittsburgh in 1940s, which is not sustainable. So we want sustainability and energy efficiency going into the future. And also, we want better quality of life. We want to understand the things around us much better. So this is a picture, a point in the climate model that basically looks at the temperatures of the waterways of the world. A lot of processing goes into this. This is congestion. Some of the hard problems that we have require probably a lot of modeling and prediction and understanding. And a lot of people are working on understanding the brain as well. And all of these require very high performance in the end. So in future, we would definitely like high performance to solve the toughest problems, but also all of the problems we have. And both of these require different design. These are different design goals, actually. And I think one of my major interests in the future is how do we enable more personalized ways of understanding human characteristics and using them for medicine, health, and other purposes, and understanding the behavior of different species. So I think the future is also personalized and private, and these are big concerns, because this is going to be dominant in all aspects of life. People are heterogeneous, and we would like to customize the devices to the people, as well as all of these different things that we would like to do with the devices. Okay. So this lecture is really about questioning what limits us in designing the best computing architectures for the future, where the future is shaped by what I described earlier, and hopefully providing directions for fundamentally better designs and advocating principled approaches. So before I move on a little bit, I'd like to talk about applications a little bit. I'm not a person who designs applications. I design architectures. But sometimes there's this debate in architecture or in the world whether we need higher performance or more energy efficiency. And I think the best answer to this is really dream. People are dreamers, and they dream, and applications come in the end. If we stop providing the substrate, the architectures that can enable those applications, these applications will never come. And as applications push boundaries, the platforms we design will become increasingly strained, as Google has been seeing. That's exactly the reason they designed that tensor processing unit, for example. Their infrastructure was very strained because they were pushing the boundaries, doing all of that neural network processing. Let me move to something else in theory. I have to put Abraham Maslow over here also, because another reason why applications come is because humans obey, at least loosely, some of these principles as well. This is Maslow's hierarchy of needs. At the bottom, we have safety, security, physiological needs. On top, you go into self-actualization. And I believe you can argue with all of this, but sometimes these get mixed as well. But I will use this to motivate reliability and security, because if you're not reliable and secure, it's very difficult to think about a neural network making yourself much more efficient in the future. So this is an outline of what I will try to cover. I will first talk about fundamentally secure, reliable, safe architectures, and I will really mix these three things, because I believe these things are very interrelated in today's world. I'll talk about energy efficiency and how to achieve it fundamentally. So I'll talk about memory-centric architectures. Probably we will not have time to talk about architectures for genomics, medicine, and health, but I'd be happy to chat about that. So let's move to this first one. This is the Tacoma Narrows Bridge again. How do we build architectures that do not break like this? Reliable architectures that do not cause security problems. By the way, fortunately, there was only one loss in this example, and that was a little dog that got strained in the car that someone actually tried to rescue from this event, but they were not able to rescue because the dog didn't want to come out of the car at that point in time. So different people have different notions of safety at different times, but a global view might help sometimes. And this is another, this may be very safe for these guys at the moment, but then something may happen and you may actually lose the security that you have. So I view security as really preventing unforeseen consequences. So without a principled design, it's very difficult to prevent unforeseen consequences, in my opinion. So in computing, and more specifically in computer architecture, I believe we do not seem to have the design principles for guaranteeing reliability and security. And I will give you an example, and this is something I would like to tackle going into the future. But I will talk about first our focus. My focus will be on main memory. If you look at memory, it's really a critical component of all systems. You need some sort of memory to store the data. And whatever computing unit that you put over here, it could be an Intel processor, it could be an FPGA, reconfigurable computer, a GPU from NVIDIA. It doesn't matter. They all need this data storage. We will come back to that data storage later on. But this system must scale in many, many dimensions if you want to maintain the performance growth and the technology scaling benefits that we've been used to for a long time. In size, in technology, in efficiency, cost, and the algorithms we use to manage it. And we're having problems with this system. Basically, as memory scales down to smaller sizes or higher capacities, it becomes unreliable. And this is very fundamental. Regardless of whatever memory you have this problem. So this is based on a paper that we wrote with Facebook. One of my students interned there and examined all of the servers they have worldwide. And this is really a lot of servers, and they didn't allow us to put the number of servers and the amount of memory, because that apparently affects Facebook's stock price if we actually publicly disclose it. But if you look at this, the key takeaway is, after analyzing all the errors that we see, as chip density grows, server failure rate also grows. And the intuition is that you get quadratic increase in capacity. So memory is becoming less and less reliable. And if you don't understand that 1.00, I'd be happy to talk about that separately. This is normalized across many, many things. This doesn't mean that all of the servers are failing. OK, so why is it the case? Basically, cells are getting closer to each other, and they're interfering with each other. And the memory is really built based on this little circuit, if you will. This is the DRAM, dynamic random access memory. It stores charge in this charge storage device, the capacitor. And it needs to be accessed through this access transistor and the bit line and the sense amplifier. For this to work correctly, this capacitor must be large enough for reliable sensing, and this access transistor must be large enough for long data retention time. You need to retain data. Just like human memory, this needs to retain data. The problem is data leaks out of these cells over time, so you need to refresh the circuit. As you reduce the size of these circuits, both of these properties become difficult to maintain: reliable sensing and high retention time. So the cell becomes much more vulnerable to outside effects. So we've been looking at this. We've been testing memory using this infrastructures like this to understand such issues, the scaling limits of memory. And we found a curious thing in actually 2012, but the paper got accepted a little bit later. We found that you can actually predictably induce errors in most DRAM memory chips that are outside in the field today. This is a row hammer problem, as it's known today. Basically, you have a simple hardware failure mechanism that can create a widespread system security vulnerability. And people write things like this: forget software, now hackers are exploiting physics, which I agree with, because it's really a physical phenomenon that's happening. Let me try to explain what this is. Basically, memory is composed of these rows of cells. Think about that cell replicated many times, and you have a row that's large, let's say 4 kilobytes. And if you want to access one row, you need to apply high voltage to that entire row. This is, you basically do an activate. Now, if you want to access something else, you apply low voltage, close the row. So if you read, close, read, close, read, close, read, close, read, close, read, close, many, many times before the same row, before the cells get refreshed in memory, it turns out adjacent rows get interfered with, and some bits that are stored in adjacent rows flip. Now, this happens because these cells are too close to each other. They're electrically interfering, and the interference is not isolated. And you get these errors in memory. This is not supposed to happen, because these rows may belong to completely different applications. Somebody else's data may be actually destroyed by this. Or, worse yet, some security-sensitive data may be destroyed by this. So we call this a hammered row. We call these the victim rows. And we showed that repeatedly reading a row enough times before memory gets refreshed induces this disturbance errors in most real DRAM chips you can buy today. So what is most? More than 80% of the chips we've tested were vulnerable to these errors. And this is a scaling problem because this doesn't happen before 2010. But in 2012 and 2013, all of the chips that were manufactured exhibit these errors. And it doesn't depend on the manufacturer because everybody's facing the same scaling problem. Cells are just too close to each other. So you can say that this is a reliability problem. I don't care. But I believe reliability is always intimately tied with security and safety. So you can actually write a program that exercises these errors and does that. Basically, this program is doing this, accessing these rows repeatedly. And if the chip is vulnerable, it's causing errors in the chip. And you can actually download the program and do it on your computer, but just make sure you're not doing something important, because this may actually lead to some persistent data to be corrupted. And you can actually, that program induces errors in many different types of chips, many different systems, which I'm not going to go into. When we wrote this paper, we believed that this actually caused a security problem. We said memory isolation is a key property of a reliable and secure computing system, and access to one memory address should not have unintended side effects on data stored in other addresses. I still believe this strongly. And we were actually working on an attack that could take over the system so that we could demonstrate and find solutions to it. But Google beat us to it. Google Project Zero researchers, Mark Seaborn and Thomas Dullian, actually showed that you could gain kernel privileges by exploiting this little hardware vulnerability. So I'm not going to go through this in detail, but this is directly from Google's blog post. It's a beautiful blog post. It's beautiful systems and security engineering, in my opinion. What they did was they were able to induce the errors on laptops, and they constructed an attack by taking our code and expanding it and doing it much better. They showed that as a user-level process, you can take over the entire system, basically get access to all of the data on that system, which I think is fascinating, because with that little bit flip, you can go all the way to taking over an entire system, bypassing all of the security measures that we have in the software. OK, so this people start calling this the row hammer vulnerability and drawing pictures like this. Is this the end of the memory? Or I don't believe that's the case. But I really like this quote that somebody has on Twitter. Basically, if you would like to break into an apartment, go to the neighbor's door and keep banging on the door. And the perturbations that you cause because of that banging magically opens the adjacent door. I think that gets to the essence of it. There's interference that's happening between the two doors over here. So other people later took this, and they basically showed that you can gain unrestricted access to systems of website visitors by doing remotely, causing these errors remotely. Or they could actually gain control of a smartphone deterministically. And these are pictures from the Met, and they're beautiful papers that are written on this topic later on. And maybe it's better to have a computer that you break like this instead of someone else breaking it for you. But this is actually the fun part of it. So fixing the problem is interesting, and I will talk about the fixes a little bit. But today's fixes are not satisfactory. For example, Apple released a software patch which increased the memory refresh rates so that the memory gets refreshed more often, which means that you consume more energy and have less performance to fix this reliability and security problem. I think this is perhaps the most viable fix that exists today, but it's not the perfect fix. So I believe we need better solution directions. I'm not going to talk about our solutions. I'd be happy to talk about that separately. But we would like to have principled designs, fundamentally secure computing architectures, where we do not have this problem to begin with. And how do we do that? I think there are 3 steps, I believe. We would like to understand first. I don't believe we understand the systems we design today. We don't have good methodologies for failure modeling and discovery, or threat modeling and discovery. And we would like to do that modeling and prediction based on real device data. And I believe this is really interdisciplinary. It's not just the DRAM manufacturer or device manufacturer's problem, because there are a lot of methods that we've developed in computing that could help this. The second is we would like to architect. We'd like to have principled co-architecting of the memory and the system, good partitioning of the duties across that stack that I showed you earlier. And we'd like to have good design and testing methods, online testing methods, in fact, that have good coverage of these faults or security vulnerabilities, and they need to have good interaction with system reliability methods. So I think understanding is facilitated by this kind of infrastructures. We have another infrastructure for flash memory, but also at the larger scale studies. So for example, if you have a data center, you have a lot of data to understand what kind of failures you're getting, and analyzing that is really important. There are two other solution directions, which I'm not going to go into a lot of detail about. One is new technologies, and I think this is really important. Can we somehow design a new technology that doesn't have these problems and replace memory, DRAM with that? Non-volatile memories are very interesting from this perspective. Phase change memory, memristors, different devices are really important to develop, and I'd be happy to talk about that separately. Unfortunate thing is, as memory scales down, all of these devices have similar problems. So I believe these problems are very fundamental. The second direction, which I believe is very interesting from a computing perspective, is embracing unreliability. So if we cannot design all of the memory, all of the data storage that we have in the world to be reliable completely, maybe we design a critical part of it to be very reliable, and the mass part of it unreliable, and somehow design the systems and the applications to tolerate this. I think this is really interesting today, especially with the applications that are very tolerant to errors, like machine learning applications that consume a lot of data, but they're statistical in nature. So another bit flip may be just an error in the data. Genomics is similar to this, I believe. So I think regardless of these two, maybe there are other solutions also, but I believe fundamental solutions to security require co-design across the hierarchy. And I don't think we can get away with punting the problem either here or here. We really need to design across the stack. OK, so that's a big challenge and opportunity for the future, in my opinion. Let's move to the next one, more fundamentally energy-efficient architectures. We'd like a future that looks like this, beautiful like Switzerland or the Seattle area, and not like 1940s Pittsburgh, probably. And I will go back to Maslow's theory over here of hierarchy of needs. And you may argue today that reliability and security is not the most important, but an everlasting battery life is the most important thing for human life today. Of course, it's a joke, but it's interesting that people have tackled this hierarchy later on after 1943, and they actually moved things around, and they actually said, depending on the situation, your needs may change as well. So there's a lot of heterogeneity that goes here. So this may be really important for your security at some point in time, right? I believe I read enough reports where a cell phone saved someone's life during an attack. So if you don't have that battery life, you may not have your life saved. OK, so but it's clear that we want a sustainable and energy-efficient future. And how do we actually achieve that? I will posit, and I will later show that data access today is the major performance and energy bottleneck. We're moving to this huge data deluge, if you will. We have so much data, but we want to be able to access it. The problem is it's really the bottleneck today. And I will again posit that our current design principles cause great energy waste in terms of how we treat data, how we move it all over the place, instead of not moving it. Basically, today, if you look at a small-scale platform and a large-scale platform, processing of data is performed far away from the data most of the time. And let's, before I show you some example numbers, let's think about a computing system a little bit. There are three key components to a computing system. You want to be able to do computation, you want to communicate, and you want to store data in the storage or memory system. And this is my student's cartoonish picture of it. Basically, you have a computing unit, memory and storage unit, and a communication unit. How do we design these today? Computation today is done only in the computing unit. So if you look here, there's a storage unit, and there's a computing unit. But storage unit does nothing but store the data. So we're overwhelmingly processor-centric. And this worked out really well because of this paper by von Neumann and friends in 1946. Because it was easy to program. But this also caused a lot of issues, in my opinion, in terms of energy efficiency. Today, we're overwhelmingly centric in this, and we optimize that computing unit. All data goes into this computing unit, regardless of wherever it is. It may be in a completely separate computer. If this computer wants that data gets communicated all the way to that computing unit. And this comes at great system cost, because if you want to move that data, that's high latency. And people design these processors to be heavily optimized such that the application doesn't see that latency. The user doesn't see that latency. It's considered the master. As a result, there's a lot of optimization that goes into it so that you don't see that latency, which means there is a lot of system cost that comes with it. And data storage units, on the other hand, are treated as dumb slaves, and they're largely unoptimized, except some that are on the processor die. Yet, it's really the memory system. It's really the data storage that's the bottleneck today. This is actually a quote from Dick Seitz, who designed the Alpha 21264, which was really the highest performance machine of its day. And he figured out that you could easily do a lot of instructions per cycle when you design the processor. But when you need to access memory, the number of instructions you process in the processor it goes down to 1/10, as opposed to 4 instructions per cycle. So if you examine a modern Intel processor, this is actually from my dissertation presentation, we've examined a large number of workloads on an Intel processor, and we've shown that more than 55% of its time, this processor is just waiting for the data, not doing useful work. This green part is the part where the processor is doing useful work. The rest of its time, it's waiting for the data to come and to be fed into the processor. So let me tell a little bit more about the perils of processor-centric design. This leads to grossly imbalanced systems, because processing is done only in one place today. Everything else just stores and moves data. So data moves a lot. And if you think about the small-scale system, this is the case. But if you think about a large-scale system also today, we have a lot of these sensors everywhere. Does it make sense to move the data into a data center to be processed? Or should we be doing more processing somewhere else? So this is energy inefficient. This is low performance as well, because you need to move the data to do the processing. And this is complex. And this also leads to an overly complex and bloated processor. You may say that, oh, we designed different accelerators, but that also increases your complexity, because you need to now tolerate the data access from memory, and you need to build complex hierarchies and mechanisms to do that. Again, it becomes energy inefficient, low performance, and complex. This is my cartoonish picture of a little platform today. If you look at it, I have only one point here, really. Only these red parts that are labeled as cores are doing processing. Everything else, the caches, the interconnect, other caches, memory controllers, other interconnect, other memory, other storage, everything else is dedicated for data movement and storage. And even if you look at this red part, most of it is really dedicated to data movement and storage inside. The computation units are a very little fraction of today's systems. So we're really designing these systems to move and store data, and we're doing that a lot. So let me talk about the systems trends a little bit. If you look at systems, applications are increasingly data hungry, so data access is a major bottleneck today. And energy consumption is a key limiter. I don't need to give examples of this. But let me focus on this. Data movement energy today dominates the computation energy. This is especially true for moving data from off-chip to on-chip. I'll demonstrate this with one slide that I borrowed from Bill Daly from his keynote at High Peak. Basically, he looks at the energy consumption of doing different things on a chip or off a chip today. Doing 64-bit double precision arithmetic floating point on a chip today consumes only 20 picojoules. On the other hand, if you look at data access from memory, DRAM, the closest memory that you can have off chip is about 1,000 times more energy than that complex addition. So given this, does it really make sense to, if you want to do a single addition, does it really make sense to bring two values, go to the memory twice, do the addition, and write the data back again? You basically consume 3,000x energy compared to the addition itself just for moving the data. Wouldn't it be more reasonable to do the data processing inside the memory? The problem is we don't have that ability today. So I believe we need a paradigm shift today to enable computation with minimal data movement, compute where it makes sense, where the data actually resides, rather than doing the opposite thing, and make computing architectures much more data-centric. By the way, let me actually go back to here, because you may say, who designed this thing, right? This doesn't make sense. This is really designed based on the precedent. In 1940s, the cost of this arithmetic operation was about 60 times higher than the cost of the memory access. So in 1940s, it made sense to move the data all the way to do the arithmetic. But today, we're not in 1940s anymore. OK, So what we would like to do, we'd like to enable in-memory computation. And this is just a pictorial way of looking at it. We'd like to do in-memory X. X could be database processing, graph processing, media processing, anything you would like. And we'd like to be able to tell memory or ask memory to do functions for us. And the memory, if it can do it, it can provide the results. And we'll have a more balanced processing system because all of the data that you want, hopefully, resides over there, and you're not moving the data. So there are many, many questions over here, which I'm not going to go into here. How do you design the memory itself? How do you design the processor chip, given that memory is capable of computation today? How do you design the software interfaces? How do you design the system software and the languages such that the programmer can take advantage of it? And the algorithms, given that memory is doing computation today, and computation is not the most important thing that we have in the system. So this also motivates design across the stack here. So let me give you a couple of examples so that hopefully there's some hope into doing something like this. Let's start with simple, not even operating on data, moving data. Moving data is something that's done in many, many applications today. It's important for a lot of things. Google actually published a recent paper showing that across many of its workloads, 5% of the cycles is spent on just moving the data. But these operations, there are other operations that move the data, but these operations are explicit operations. So how do we do it today? Today, if we would like to move data from this memory location to this memory location, let's say 1 megabyte or 4 kilobytes of data, we move it byte by byte all the way into the processor. We move the destination byte by byte all the way into the processor, do the copy, and write the result back. This is high latency. This causes high bandwidth utilization in this component over here, causes a lot of pollution in the system, and cause unwanted data movement, because you may just want to copy the data from one place to another. Actually, if you think about initialization, if you want to initialize a large amount of memory, when you start up the system, initialization is essentially moving data, writing zeros. And we're going through the processor to do all of that writing zeros. Today, it costs a lot of energy and latency. Wouldn't it be nice if we were able to tell the memory controller, do this copy and don't bother anything else in the system? And that's the idea. If you do that, this is low latency, low bandwidth, no pollution in the rest of the system, no unwanted data movement. And it turns out we can do that, reduce that latency, 1,046 nanoseconds latency, to only 90 nanoseconds, and energy from 3.6 microjoules to 0.04 microjoules. So I will not go into how you do this, but basically, with little modifications to the DRAM chip, activating a row, and then activating a destination row, we can do this with negligible hardware cost today. But the mentality today is DRAM doesn't do anything. It's dumb. It's a dumb slave. It doesn't do computation. It doesn't even do data movement internally. So basically, the latency and energy savings, you don't need to understand all of this, but basically the latency savings that you get is about 11.6x, and you can optimize it. But the energy savings are even larger. Memory energy savings are almost 2 orders of magnitude, because you're not moving the data across large interconnects. So similarly, we can actually support in DRAM and or not. So you can actually have a functionally complete engine in DRAM at low cost, using analog computation behavior of memory that exists today, and at least a 30 to 60x performance and energy improvement for those operations. Of course, the system level improvement depends on how much you actually perform those operations in your application, right? And I believe there's another new memory technologies enable even more opportunities. For example, memristors or resistor RAM, they have the ability to do operations with minimal data movement, almost in place. But I will not be able to talk about that in detail right now. Let me give you another example, which is more on the complex side. I gave you very simple, how do you do data movement and or more efficiently. But if you look at a big application, graph processing is an important application. And when we first started thinking about in-memory computation, graph processing was a no-brainer to look into. And this is actually data from 2015, so maybe these numbers have increased significantly today. But graphs are everywhere. It's used by many computing applications, and I don't even have genomics here, and genomics is increasingly graph-based. And scalable large-scale graph processing is actually challenging. You cannot throw processing elements to it. We've not done that study. If you actually quadruple the number of processing elements you have, you get only 40% speed up. Ideally, you would like 4x, right? So this is actually a really interesting computation, which I'm not going to go into detail, but I will tell you 2 properties of this computation. You get frequent random memory accesses, because you look at the neighbors in your graph, and these are usually randomly located. and you have very little amount of computation. This is the PageRank computation, which is ranking web pages, for example. So we've designed the system, which basically consists of a logic layer underneath memory. So you have very high bandwidth access to memory and low latency and low energy access to memory. And we've interconnected these devices and laid out the graph on top of it. And there's a lot of detail that I'm going to skip. I'm just going to go into the potential benefits. But you specialize the logic that you have over here for graph processing, and you get a lot of benefits. Let me compare the systems. These are today's systems that you have, and the bandwidth you have to memory is limited in today's systems. Tesseract, the system that we have, it looks different because it's doing processing in memory. Memory and processors are not separate as in today's systems, as you see, but you have memory and processors inside the same thing over here. As a result, you get 8 terabytes per second access within a single platform. So what are the performance benefits? Again, the thing to focus here is on average, across 5 graph processing algorithms, you get almost 14x performance improvement by changing the model that you have. Of course, it comes at a cost, but you cannot achieve this with today's systems where you move the data into the processor all the time. And because we can exploit the memory bandwidth benefits that you have. So the energy benefits are also commensurate. Basically, you can get 8x energy reduction, even without looking at the core's processing units in the baseline system over here. I believe there's more to be done. This is not the optimal system. I'm not claiming that. I believe there's a lot more potential in this area. So hopefully this motivates. We'd like fundamentally energy efficient, i.e. data-centric or memory-centric architectures going into the future. I have a couple of minutes, so maybe I'll go through this very quickly then. So genome sequence alignment, I believe, is very interesting. There's a lot more in this topic, but I'll pick genome sequence alignment because we do some interesting things over here. There's a lot that goes into it, but this is also a computational problem. And we're really interested in how to map the sequenced little fragments into a reference genome, or do the mapping across different genomes so that you can compare different genomes, like in this picture. It turns out we're bottlenecked in mapping. Today, we can actually, with sequencing machines, we've overcome the bottleneck. We can sequence things really fast. We can get 300 million bases per minute, but our processing is limited. We have only 2 million bases per minute. The question is, how do we actually make this faster? And if you have questions, I'd be happy to take them later on. There are principles here. Let me conclude before the bell rings. So this is a quote from a famous architect, not a computer architect. This architect says, we should design architectures based upon principle and not upon precedent. Can anybody guess who this is? I'll give you a hint. If you were in Pittsburgh, probably you would have guessed. But this is Frank Lloyd Wright, the famous American architect. And if he had designed architectures based on precedent, he would have done another one of these. But instead, he did this. This is Falling Water. It's considered a masterpiece in architecture. Similarly, if another famous architect wanted to design a train station, they would have designed this, perhaps, based on precedent. But somebody designed this train station. Can anybody guess what this one is? Yes, right? This is Stadelhofen. And there is principle in it. And you can see the principle in something else that this famous architect designed. This is New York, and this is the Oculus. Can anybody guess who this architect is? Yes, this is Santiago Calatrava, who's an ETH alumnus. No. So basically, I'm advocating more principled design. It's time to design principled computing architectures to achieve the highest security, performance, and efficiency. And it's time to discover design principles for fundamentally secure and reliable computer architectures, and design complete systems to be balanced, as opposed to little components to be balanced internally. Basically, more data-centric or memory-centric architectures. I believe the expanded view of computer architecture can lead to orders of magnitude improvements. I've given you some examples, but I think they can be much bigger, and enable new applications and computing platforms as well, and other things that humans may end up dreaming of. So I think the future is very bright in the end. Regardless of the challenges that we have in the underlying technology and the overlying problems, if we take an approach that's more expanded, we can do much better. So thank you.